Hello, so we have some physics topic 5, paper 1 questions here, so let's start going through them. So two 6 ohm resistors, here and here, are connected in series with a 6-volt cell. A student incorrectly connects an ammeter, and a voltmeter is shown. Okay, so we know this is incorrect because you're not supposed to put an ammeter in parallel, and you're not supposed to put a voltmeter in series. So we know ideally a voltmeter has infinite resistance, which implies that there is no current at this point, because no electrons can get through because the resistance. So hence current is 0 here. And that means that current is also 0 here because this is just in series. And we can apply junction rule here. So the current here plus the current here equals the current here, which is 0. So 0 plus 0 equals 0. So we know it's A or B. And now we can find the voltmeter reading. So we know that current here is 0. We know that current here is 0. Okay, so I'm just going to write down Ohm's law. V equals I R. We know that this I here is going to be a constant value. I'm not going to write down 0 because that kind of ruins it. But we know that voltage is proportional to the resistance. Okay, so first we have 6 ohms, and then we have infinite resistance here. So we know that this has to be proportional, the voltage has to be proportional to the resistance. So that means that, well, we know that this is a total of 6 volts in the system. So we know that this would be 0, this would be 6. Well, you just have to remember that whenever you play around with multiple things in series, you have to make sure that the resistance that a certain resistor that's in the system applies, that's going to be proportional to the voltage that it essentially consumes, the potential difference before and after that resistor. So we know that the answer has to be B. Hopefully that explanation wasn't too confusing. Okay, let me clear this board. Okay, so the diagram shows a potential divider circuit, okay, in order to increase the reading on the voltmeter, V, and then we have 4 conditions. Okay, so we know this is a light-dependent resistor, LDR, okay. So essentially what we have here is we're trying, so I'm going to write down V equals IR again, okay. So what we have to do is I'm applying this V equals IR for this portion of the circuit, okay? So we're trying to increase V, and all we can do is change R essentially. So we have to also increase R. So how do we increase the resistance of a light-dependent resistor? So we can do that by decreasing the light intensity, and you have to remember that. But essentially, when it gets darker, the resistance of this resistor will increase, and that will increase the potential difference that occurs at the resistor. So the answer is D. Okay, this is not topic 5, so let's skip that. Which diagram best represents the electric field due to a negatively charged conducting sphere? So we know that we can kind of test for the electric field with test charges, and test charges are positively charged, and we know that positive charges are attracted to negative charges. So we have to look for arrows that go towards the sphere, so C or D. We know that the net electric field strength within the conducting sphere is going to be 0, so it has to be C, cannot be D. Okay, so a point mass carries a positive charge plus Q and is at rest in a magnetic field. The field is in the direction shown. The magnetic force acting on the charge is, okay, well, we actually have a formula and it can become very intuitive once we look at it. So we know that F is force, B is magnetic field strength, I is current, L is length, and then sine theta, that's the angle between the magnetic field and the current. Okay, so actually this charge is at rest. There is no current. I is equal to 0, therefore F is equal to 0, so 0 is our answer. Okay, let's look here. So the tungsten filament of a lamp has a cross-sectional area A, length L, for a potential difference V across the filament, and the current is represented with I. The resistivity of the tungsten equals. Okay, so we have a formula. So resistivity equals resistance multiplied by cross-sectional area over length. Okay, so we don't actually have R in any of our solutions, but we know that I'm going to go back here. V equals IR, so that means that R is equal to V over I. There we go. So we just have to look for that. So we have to look for VA over IL. VAO, that looks like the first answer here. So that's our answer. Okay, so which of the following is the correct unit for EMF? Okay, so we know that EMF, it's similar. It has the same units as voltage. So we can look here. We're just applying units here. So we know that, well, we're looking for volts, but hey, that's not there. So we can just use this. We know work is in joules. We know that Q, the charge, is in coulombs. So it's going to be this answer right here, joules per coulomb. Okay, next question. Which of the following correctly gives the resistance of an ideal ammeter and the resistance of an ideal voltmeter? We have to remember this. We know that it would be, ammeter would be 0, voltmeter would be infinite. Okay. Gravitational, oh wait, that's not our topic. Okay, next question. A hollow metallic sphere is negatively charged. Which of the following represents the electric field? As I mentioned before, and positive test charges are attracted to negative charges, so we're looking for arrows that go towards the sphere, so B or D, but we know it's not D because the net charge, or net electric field strength within this sphere is going to be 0, so it has to be B. Okay, so in the diagram, a long circuit carrying wire is normal to the plane of the paper. The current in the wire is directed into the plane of the paper. Okay, so it's going into your screen. So we can use the right-hand rule here. Okay, so I don't have a camera, but I'm taking my right hand and I'm making a thumbs up essentially, and I'm pointing my thumb towards the X. It's going into my screen. Okay, and you can imagine your fingers as curling around that thumb, and they're currently curling around clockwise. So imagine you're drawing circles. You're drawing circles around here clockwise. So at point P, this magnetic field, that's going to be facing W, because if we draw a clockwise circle here, that's gonna at that particular point, it's going to be in the direction of W. So our answer here is W. Okay. A point charge of magnitude 2 microcoulombs is moved between points X and Y. Point X is at a potential of plus 6 volts, and point Y is at a potential of plus 9 volts. The gain in potential energy of the point of the gain in potential energy of the point charge is. Okay. So what we have to do here is, well, we can use this formula right here, I believe. Yes. So voltage equals work done over charge. Okay, so we know our charge is going to be 2 microcoulombs. Okay, and we know, well, our voltage, it's gonna have to be the change. It's gonna be a change of voltage, or not a change of voltage, but rather a change of potential difference. Okay, so we know that, or not a change of potential difference, just a potential difference, and we know that we'll call this V2 and this V1. So V2 minus V1 equals V. So 9 minus 6 is 3. So we know that this is 3, and this is 2 microcoulombs. So 3 volts and 2 microcoulombs we can multiply, and that would be 6 microjoules. So that's our answer. Hopefully my explanation was okay. So now we have a resistor of resistance 12 ohms is connected in series with a cell of negligible internal resistance. The power dissipated in the resistor is P. The resistor is replaced with a resistor of resistance 3 ohms. What is the power dissipated in this resistor? Okay, so we can look at this formula right here. P equals V squared over R. I'm going to write that down. Let me just delete this. P equals V squared over R. we know that v squared, that's going to be constant because our cell isn't changing, but these two variables are. So we start off with 12 ohms as a resistor, and that results in a power of P. Okay, but now we reduce our resistance by a factor of 4, so we're dividing by 4 essentially. So if we divide this value by 4, we're going to actually end up multiplying P by 4, so that's going to be D. The electromotive force EMF of a cell is defined as, well, I'm looking at these answers, and at first you might be tempted to do D, the potential difference across the terminals of the cell, but that's actually not true, because that doesn't account for internal resistance. So actually, this is actually tricky. What you have to do is you can use this, I believe it's right, should be somewhere here. Yeah, okay. So what you have to do is you actually have to use this formula right here. P equals VI, and you divide by I on both sides. The power supplied by the cell per unit current from the cell. And this actually accounts for internal resistance, because we know that electromotive force is slightly different from voltage. So this is actually our answer. And this one's actually kind of tricky. Yeah. So this is not topic 5, so let's skip that. Okay, I guess I'll make this our last question. 3 positive point charges of equal magnitude are held at the corners x, y, and z of a right-angled triangle. The point P is the midpoint of x, y. Which of the arrows shows the direction of the electric field at point P? Well, we know that this charge right here would be positive. This charge here is positive. I believe that. Wait, let me read this again. Oh yeah, sorry. We can essentially charge the electric field by putting a test charge here, and we know test charges are positive, and positive charges repel from other positive charges. So let's imagine it right here. So we know that this positive charge right here would want to push it in the direction of C, but we know this charge here would want to push it in the direction of A, and since this is the midpoint, the forces would be equal and they would actually cancel out. So the only charge we have left is Z or Z, and that would actually repel repel a test charge in the direction of B. So the direction of the electric field at point B, or point P, would be in the direction of B. So yeah, I hope you gained some value out of, I guess, me going through some paper 1 questions, and I hope all of my explanations are okay. Thank you for listening.